So my name is Preston Smith. I'm the Executive Director for the Rosen Center for Advanced Computing at Purdue, and I'm going to tell you about the data-intensive research that happens at Purdue University and how DDN Storage helps enable that. So I've got a couple of slides here that I'm just going to, really high level, tell you a little bit about Purdue. If you want to learn a bit more about Purdue and all the great things that happens there, it's only like 20 feet away. You can go over there, talk to our team, learn all about the great things happening there. So Purdue's, for over 150 years, has been pursuing innovation, and generations of Boilermakers have been leaving their mark in small steps. You're going to hear this word a couple of times, because one of the things that Purdue has been famous for is astronauts. So Neil Armstrong's step on the moon and the giant leaps and small steps are a common theme as we talk about all the things we do at Purdue. So Purdue is a member of the Big Ten. We're in the state of Indiana. So despite sounding like a small private college, we are a large land grant institution. So we're a top 10 university in the U.S. Over 135 countries are represented among our student body. Purdue, like I said about Neil Armstrong, is a cradle of astronauts. We've had 26 astronauts come from Purdue and fly into space. And to get into a little bit about computing. So Purdue this last year unveiled an initiative called Purdue Computes. Purdue was the first university to found a computer science department in 1963. They're celebrating their 60th birthday this year, and our center actually was formed alongside that computer science department to operate and provide the computers needed to enable computer science. So this Purdue Computes is really investing more in computer science, computer engineering, and elevating AI as a pillar of research at Purdue. One of the strategic research initiatives happening at Purdue that we support computationally is aerospace. I'm not going to go into a lot of detail about the substance of these professors' research, but this is just to give you an idea of the breadth of things that we support. Again, if you want to learn more about it, the Purdue booth would be a great place to talk about the science that gets enabled. Hypersonics is a big area of focus in Purdue. National defense research and aerospace as a major engineering institution is one of our key focuses. In addition to engineering, agriculture and life sciences is an important thing at Purdue. So environmental sustainability, environmental science, remote sensing is a key area of research. Some of these have been done about understanding and counting the number of trees in the world, or making sure that crops can grow in other parts of the world just to feed our growing population. Alongside Purdue Computes, Purdue is announcing an Institute for Physical AI. You might say, what exactly is physical AI? Physical AI takes all of the physical sciences and engineering things that Purdue as an engineering institution is renowned for, and using AI to help build on that and enable new discoveries. And then finally, digital agriculture, which I talked about with the counting of the trees. And then finally, at a place like supercomputing, I would be remiss to not talk about semiconductors. Purdue is a very large electrical engineering department. One of the things that we enjoy about supercomputing is the number of Purdue alumni that we see coming over to the booth that are working at companies all over the show floor. So Purdue is investing in semiconductors. The CHIPS and Science Act is enabling all sorts of workforce development activities, training people to help develop semiconductors and high technology in the future. So how do we tie into all of this? So our center operates what we call a community cluster program, which provides high-performance computing and data to Purdue faculty from all over the university. So the general strokes of it, we build an HPC system roughly every year. We support about $2.5 million of faculty investment every year. The general rules are that you get out what you put in. So this keeps faculty from building small clusters on their own, putting them in their labs, having their grad students operate them, and you get access to what you bought. But the real value add is that you can share everybody else's. If James here is a faculty member and he's not using his resource, my grad students can run on those compute nodes and get more value out of the cluster than just what I paid for. But the most important thing, you as a professor don't have to do the work. You can write papers, your students can graduate, and we in the Research Computing Center do all the work for you. So this has allowed us to build some very powerful machines over the years. On the top 500 list, we've had a number of machines that have made that list, culminating with Conte, which was built in 2013, which reached number 28 in the world. The constituents of the program are very widely represented. Of course, at the top, it looks exactly like what you would expect at a place like Purdue. Mechanical and aeronautical engineering, high energy physicists. Of course, they need tons and tons of computing. But as you look down the list, democratizing access to high performance computing is happening at Purdue as well. We've got botanists and economists and food scientists and psychologists, all of which are increasingly needing high performance computing to analyze their increasing amounts of data in their own research. So the cluster program provides lots and lots of resources, shown here by all of the CPU hours that we deliver over the years. But most importantly, it's great seeing these up and to the right graphs, right? Those show lots of growth. But really, it comes down to impact. The cluster program provides tremendous impact to researchers at Purdue. On the left there, we can see the graph, the trend of the number of students who use high-performance computing to get their degrees and to get their dissertations done. Culminating with, we've got data, and actually the 2023 data I've got since I made this slide, 27% of the PhDs awarded at Purdue went to people who used high-performance computing. So can you imagine that here in the 21st century? How important it is to have access to those resources to get your PhD. It would be like if you don't have high-performance computing, it would be like going to a university to study biology if you don't have microscopes and pipettes. So I'm very excited to see that number go up every year. But in terms of the research enabled, we can see the trends going up over time. Years ago, that the non-computationalists did the most of the research in terms of dollars at Purdue. But starting in about 2014, right after Conte was built, interestingly enough, that trend goes up. And now we see 64% of all the research happening at Purdue is by researchers who use our high-performance computing systems. So Cycles, of course, gets all the glory in high-performance computing, right? We saw the top 500 list was announced yesterday. All sorts of great things happening in accelerators and CPUs. But storage, we're here at the DDN booth. Storage is one of the key things that makes that possible. If you build a machine that's great in compute, but with inadequate storage, the impact is going to be much less for the users. So we've had a broad journey with providing storage in our high-performance computing systems over the years. The early days of our program, like with our seal system in 2008, it was much less robust than it was today. We had lots of small NFS servers, not National Science Foundation network file system. We had lots of NFS systems, which were fine at small scales, but as the program grew, it became clear to us that it was inadequate, and we needed to find different technologies to enable this. We actually got our first DDN system in 2005, which was a whole 25 terabytes. It was about one rack worth of storage. It was a S2A 8500 running the iBricks. So if any of you remember the iBricks file system, that was our first foray into a real high-performance computing file system. But we had a small crisis with our users. We were trying to run Gaussian against the NFS file server that led us we need to fundamentally rethink what we're doing. So we've had a long partnership with DDN following that, and this table kind of shows all of the DDN systems that we've deployed over the years. Starting back in 2010 or so with our Hansen cluster, small clusters with small quotas, all the way up to today with our brand new Negishi cluster that was deployed earlier this year, where we're nearly 10 petabytes of raw capacity and 200 terabytes per user. One of the things we've really set out to doing with our storage strategy is we want the storage to be there just as a thing to enable the researchers. If they have to ask for more resources just to start doing their work, then we've not provided enough resources for them. We want to remove friction for getting onto resources as much as possible. So a little bit about the overall landscape on research data at Purdue. We've kind of done an analysis of what's all happening at the university, in terms of data storage-wise. Everything from cloud storing, like your Dropbox or OneDrive, all the way up to our high-end HPC. And we can see that here in the very low end, this is things like OneDrive and Box. We have a whole 1 petabyte of data in there. among 80,000 users. So it's a much different profile. You have a very broad user base, but very small needs. Maybe it's around just like data sharing or working on documents together. There's the enterprise NASs for desktops and things like that. But the vast majority of the storage at the university is held within our center. 90 petabytes in total of storage, including what's in our tape archive. Over 50 petabytes of that today are running on DDN hardware. So I think that's a great testament to the value that we get out of DDN Exascaler. At the college level, there's some resources there, but one of the challenges that we always have in higher ed is that do-it-yourself. It's like, what exactly is out there that we don't know about? Because faculty, they're in the column 5 there, they'll find a way. We see people keeping, they've got the USB drive. This has got my dissertation and all of the data supporting it that they need to keep track of. Maybe they have it in USB drives because it's a little bit larger and they're sitting there on their desktop. They've maybe got dubious networking setups, or they've built the file server that runs their department out of whatever parts that they pulled together. Maybe they have it in privately owned Dropbox. So how do we solve this problem? So we developed a service about 10 years ago now called Data Depot. For these common sets of data. I have data that needs to be persistent. I have data that can't be purged, but I'm actually actively working on it. I have money to spend on storage, but you don't have a product to sell me. That was an important problem to solve. Or the one we see at every university is my one grad student had the one copy of the data that my lab works on, and he went back to China for the holiday, and nobody else can do any work. So the Depot helps solve a lot of these problems by providing a single space oriented around the PI's research lab, where they can keep common data sets, they can keep applications and keep all that stuff and solve all these problems. So it's built on DDN SFA hardware, 2 generations now. It has features like snapshots and multi-site replication. We use Globus for data transfer, but the goal there is to allow for frictionless use and movement of data. So the strengths of this is it's very scalable. The DDN hardware provides lots and lots of bandwidth, lots and lots of IOPS, and it's local compute hardware. And it's a regular file system, so we're not doing anything weird like object stores or cloud storage platforms that are kind of foreign for PIs to relate to. And it's built around the common patterns that we see every PI, whether they're computationalists or not, working with. We are now thinking about our next generation. We're in the final year of its 2nd generation. It's got two sites with DDN 18Ks in each, and a 3rd disaster recovery site. So now next year we're working with DDN and our key partners on what does that look like for next year. Of course, it's going to be larger, faster, newer. Is Exascaler an option for this now in 2023 as the features in Lustre get more and more enterprise capable? Can we do things like better integrating with our libraries and their data management software that'll help us meet data management requirements coming from sponsors like the NIH or the NSF? These data management plans that are becoming more and more important. How can we lower that friction between working with data on Scratch or Depot and getting that into the archive from the librarian sense? But of course, I would be remiss to be at supercomputing and talk about all of the things that are bubbling out there that AI is creating. It's changing the world in a lot of ways for us as a computing provider. We've seen our needs for I/O resources increase a lot over our historical trends. Our Bell HPC system, when we built that in 2020, it was already a paradigm shift then for how people work with I/O in terms of the performance that we needed and the capacity that we needed. But as we see these university initiatives moving forward, like Purdue Computes, hiring 50 new faculty members that are going to be doing CS and AI, building the Institute for Physical AI, we're going to see a lot different user base. It'll no longer be people doing fluid dynamics only, molecular dynamics, quantum chemistry. There's going to be all sorts of new AI use cases that we've never seen before. So I think it's pretty clear that a purely spinning disk-based 2 petabyte file system is not going to be enough for an AI cluster. So what's that going to look like? We've just rolled out a new refresh on our AI platform based on the 400 MDX, which is going to bring in more flash on there. We're building a new supercomputer for 2024 with the goal of being in the top 100 on maybe the future top 500 list, which that's going to mean lots and lots of GPUs, lots of AI capabilities, which will be completely new AI patterns, I/O patterns that we've never seen before. So we need to make sure that our storage is up to those needs. It's expandable and modular, which we're very excited that the 400 MDX2 platform is going to allow us to do that. So with that, I am at the end of my slides here, and probably